what I like to introduce to you today is the thoroughly the black box approach, which initially we don't like to pursue for the our fluid mechanics related research. But in the end, we found that this black boxes was really nice, especially for flow control and the shape optimization related to the flow or machines or something. So we use deep reinforcement learning technique, and then I will show you these two cases using this technique. And this works done by my students, Seung-pyo Hong, Sejin Kim, and In-young Kim, and work supported by National Research Foundation of Korea and Samsung Research Funding Center funding. Okay. So I believe most of you are familiar with the concept of reinforcement learning. And the learning is basically developing a brain which learn a policy which conducting a objective action. And these techniques are basically not new, and many previous studies explored the utility of this technique. For example, the separation control over a blood body, or control over swimmer to have an efficient schooling. And also some people use this technique for shape optimization, especially for designing an aerodynamic shapes. The topics we are interested in is more challenging. As you seen earlier, the examples are basically treating relatively simpler situations, which means you can select other techniques instead of reinforcement learning. But the problems we are interested in here is really difficult to use standard or conventional well-known techniques. And then we decided to use reinforcement learning. The one case is the control of fly scale flapping robot or flyer. And this flyer has a wing which is flexible enough to be deformed by interaction with the fluid flow. And it will make a huge influence of the aerodynamic performance of the flyer. And the other case is the multi-condition, multi-objective optimization. So most of the object optimization techniques are developed for multi-objective optimization. So for example, we have objectives of something and the other, and then you make a gradient-based approach or many nice optimization in the multi-objective space. However, it was not really common considering the multiple conditions at the same time. So if you have multiple conditions and at the same time multiple objectives, then the reinforcement learning has something powerful alternative for the conventional techniques. So let me first show you the first example, the control of a fly mimicking flyer. This is a millimeter scale, actually the fruit fly mimicking flyer. And then we consider the reinforcement learning to control the maneuvering or hovering of the fly. There are many works in the development of micro air vehicles with the flapping wings, as you are all familiar with these famous robots or flyers in the late 2010s. And those devices actually are quite successful. For example, they can control their motion up to 7 meters per second of forward motion, and even making a hovering like a hummingbird, and also quite robust. And they can even recover their motion from the collision. And then it was really, doable in the real situation. However, if you go to a much smaller scale, then still we have a challenge which is not discovered by the previous work. For example, the earlier work is mostly done in the ambient environment, which means no outside mean flow. And this is something mostly dominated by the aerodynamic motion with the ambient fluid. And however, if you go to a millimeter scale, then the force generated by the flapping itself is really significantly influence the stability and the force acting on the vehicle. So we are considering such a situation. And let me show you briefly what have been done for designing a control strategy for such a motion. It's basically a quasi-steady modeling, and they actually decompose the motions of a wing in a certain component, the dominant component, for translation or rotation, and then estimate such forces independently, and then make a superposition of the force to estimate the total force acting on the micro scale vehicles. For example, using the proportional derivative or linear quadratic regulator types control algorithms. But as I mentioned, if you have a much smaller scale flyer, then as you've seen in the right-hand side animation, the flow of phenomena, the vortex generated by this motion is strong enough to influence whole aerodynamic performance and the stability. And as you know that this influence is due to the vortex generation from the fluid flow, which will be highly unsteady and nonlinear. So we should consider both the fluid structure interaction during the flight, and also we account for all the nonlinear aspect of the motions into the control strategy. So we need a real-time based realistic control strategy for realistic motions. So the idea is that we conduct both computational fluid dynamics and also structural dynamics at the same time, because we are simulating a flapping wing which has flexibility, and then it combined with the deep reinforcement learning algorithm, and then you decide a state, give a reinforcement algorithm, and then determine the action and make a circulation of this process until we develop sufficiently trained network. Still, we have a simplification, even though we don't like it. So, for example, making a full 3D simulation of a flyer is really, really expensive still using computational techniques. So we reduce the model with a two-dimensional wing, which has a motion in the two-dimensional space and also flexibility only in the two-dimensional space. However, still this motion is known well approximate whole 3D flapping motion of a fruit flyer using span-wise multiplication of the force or the moment. So we use this approach. But still, the computational cost to train using reinforcement learning to develop a control strategy is extremely expensive. So my students come up with a new, very smart idea to amplify the number of data which we can get from CFD and CSD simulations. The three types of data reproduction method can be considered. The one is translation, which means you can simulate only one single one stroke motion, and then move this motion in the X, Y, the two-dimensional space in the 10 different locations each. So we make totally 100 different variants of the same motion in the two-dimensional space. And at the same time, you can have a mirroring, which will make one another different data. And then the last one is make a rotation of the original data in the two-dimensional plane. And at the same time, you consider the rotation of the direction of the gravitation. Then the network will consider this increased data, number of data as a new data. And then the train will be accelerated. And actually it works. So this is the animation showing the training and at the same time, and then moving toward the goal. For example, the fruit flyer starting from the red square to the red star. And at the beginning, the flyer is learning how to control himself and then approach toward the goal. And you see here the different lines. For example, the green line, which fails to approach to the target, is only use the data which we can get CFD and CSD. So the number of data is so small. However, if you consider translation and mirroring reproduction, the blue line is, shows some better trajectory towards the goal, but eventually fails. Still, we see that the number of data is not enough. However, you consider all the data reproduction techniques we mentioned in the earlier slide, then the red line indicates the successful maneuvering of the flight. So this process contains the training of the reinforcement learning algorithm, and the loss function is obviously the distance between the starting point, the current location of the flyer and the goal. And this is the example we show how this data reproduction techniques were successful. The extension of this study is now considering the ambient fluid to a moving fluid. So we want to consider a more realistic situation. For that, in addition to the data reproduction technique, we also consider multi-agent learning, which means we conduct multiple CFD, CSD simulations all together and then train the algorithm considering the other simulation result at the same time for same stroke sequence. So, for example, using different background speed, so you see in the bottom, the orange, yellow, green, and blue line indicate the ambient fluid flow, or the speed of the ambient fluid flow. The flow is moving from left to the right. So the fruit flyer is trained to control himself upon the imposition of the background fluid. Now, using this information, so the flow from left to the right with a different speed, the network is trained, and we tested this trained network for untrained flow conditions with a different direction of the flow. The arrow indicate the direction of the flow, and the number is the speed of the flow. So as you see in this figure, all the cases we considered here was successful. So, you know, I don't know whether you have ever tried to develop a control scheme for such a flapping flyer before using some other techniques, but the reinforcement learning, I don't know what's happening inside the network actually, but it turns out very successful to train such a motion to the network. And we are considering even more complex situation. So we do have a unsteady background flow. So for that, we make time varying boundary conditions, And at the same time, we like to check whether this flyer actually really can control himself from the disturbance. So we impose some certain rotational disturbance at some point, or the force to the opposite direction from the motion, or change the target location from one point to the other, whether this flyer can really control himself toward the target for such a complex situation. So this is the case. Starting from the red square, we impose rotational disturbance here. He is struggling to find the goal, but eventually towards the goal. And then the star move toward the top, so you'll follow. But again, we impose another disturbance, the downward force, and then recover, and then toward the goal, and then move this star location to the right-hand side. And you see that it successfully follow the target, but the target returned back to the left-hand side, and then flow is actually oscillating in the background and overcome this flow and then control and change the target location at the center and go toward the goal. So this flyer has really successful, control strategy, not only the ambient, but also complex fluid, background fluid situation. So I showed you the application of reinforcement learning in the fluid dynamic control example. The second one, as I mentioned in the earlier, is multi-condition and multi-objective optimization. So I will briefly skip some of the slide here. So you know that everywhere we need a save optimization. For example, for designing a wind turbine blade, the objectives can be a power generation, blade loads, and acoustic noise. And at the same time, you should consider various wind conditions. So this is obviously the problem requiring the optimization of multiple objectives and multiple conditions. Aircraft wing also need an aerodynamic requirement depending on the flight condition as objective, but the conditions can be different depending on the takeoff, cruise, or landing or something. So as I mentioned, there are multi-objective optimization techniques. And then this technique is something finding a set of optimal solutions, which is called Pareto front. However, as I mentioned, there are actually we couldn't find optimization technique considering multiple conditions or continuous condition space. So our goal is to find the Pareto front, not only the objective space, but also considering the condition space. So as a target problem, we selected an airfoil shape optimization. So this problem is actually defined the state as a condition and the weight among the objectives. The objective for this problem is nothing but the CL and then CD over CL. And the condition is Reynolds number. So for that, we define the cost function as a maximization of CL and then CL over CD, and in the range of Reynolds number in this region. And to design the airfoil shape, we use Kalman-Trapez transformation method. And this requires 3 parameters for the shape and at the same time the angle of attack alpha. To determine the aerodynamic performance, we use the X-foil program, which is a very simplified, quick solution of the aerodynamic performance. So this is the actual process of the optimization. Each dot is each episode. And then you see that the vertical and the horizontal axis are indicating the objective space and the condition space. So we will fill out the point near the Pareto front, and those are the optimal locations. So at 10,000 100,000th episode, you see the Pareto front shape. You see some non-linear features and also non-convex features of the optimal Pareto front, which will be very different, very difficult to obtain using the conventional method. And those are the design parameter space using those obtained using the reinforcement learning. So above the Pareto front, this is the actual shape of the airfoil, and then the change of the airfoil depending on the Reynolds number. So we actually conducted the CFD, whether this result is really works and give a result we expected, and was quite successful. Right? So we actually use many different other research using supervised and unsupervised learning, especially for reduced order modeling and also turbulence modeling. But today, what I wanted to show you is that the application of reinforcement learning in the control and the optimization applications. And our experience is quite successful. Not only the examples I showed you, but also we have many other control and the optimization applications, but was quite successful. And we are looking at in more deeper part of the network, why this works. I don't know how it's gonna be difficult. Okay, all right. So thank you for listening my talk, and I have if you have questions, yeah, then I can answer.
Yeah, thanks a lot for wonderful talk. I'm very happy to see airfoils and flights and micro vehicle kind of thing. So yeah, any questions from the room?
I have a question regarding the data augmentation procedure used in the fruit fly. So it's interesting that you can increase the amount of data massively, right? Even infinitely if you do, let's say, translation and rotation. But is this really this a plus or a minus? I mean, I would think that if you want to reduce the data, because you are looking at the same thing just by translating it and doing the coordinate transformation, can you maybe use frame invariant input and output, and then just do more epochs of the same data again, rather than reproducing that? Isn't this going to like increase the cost? That's the thought that because my work also deal with this invariance a lot. So I was just curious what your thoughts are.
Actually, I was also really curious about this approach. When my students bring this result and this idea, I thought exactly the same way you mentioned. For reinforcement learning, it was successful because the way to training this algorithm is nothing but making chances of trial. So increasing the number of data, even though the data is essentially the same, basically in terms of physics, but the network consider every single variance of the condition as a different one, and then train himself to adapt such a different combination of variables. And we tried the data reproduction. Here I show you that 10 times in the coordinate x, y, and the theta. But also we tried the just 5 and 20, but it has some optimal number of reproduction. Increasing further is not successful. Also decreasing, we need more data. So I don't know whether 10 times of in the variable space is good enough or optimal, but in this case was successful number. Okay.
Great. Thank you for your clarification. This is certainly very interesting work. I
Right.
also read your papers in the GFM paper, and it's quite well read. Yeah. But I didn't know line of work. Thank you.
Thank you. Thank you very much.
Any other questions? Professor G has some question. You can move to.
Can you hear me, Professor Donghyun?
Yes, yes, I can hear you.
Good. I wish you come to the gist today, but I know you have a health issue. So
No, I don't have a health issue. Actually, I had a meeting yesterday, and then there was a person who has symptoms, and then when I come back to driving to home, I got a message I need to take a PCR and then stay at home until you got the result. But I got the result this morning, so I'm fine. Don't worry about it.
Oh, that's great news.
so my question is kind of following question on this topic, and this fly has 2 wings, and if you have more wings, then do you think, for example, the dragonfly, it has 2 pairs of wings, I think.
Mm-hmm.
And those kind of more complex systems, you can just add more equation and more terms, and also the data reproduction method. Then do you think expand this methodology to the more complex flight maneuvering cases?
So if you like to control 4 wings independently, so in our case, we actually, freedom of wing is only 1 wing, right? So if you like to have a symmetry plane and then like to control 2 wings, or if you consider totally, non-symmetry situation with the 4 wings, I say there's no, difficulty using this algorithm. However, you will see the difficulty in the number of data and the time of training. You need a much more, situations, combination of the wing and the interaction with the flow. So you need the data. Now, what I like to mention here is what we was really, surprised by the result at the beginning. When we started at the beginning, we consider only the, aerodynamic part of the wing and the motion and coordinate of the wing, or something, shape related information in the control. It was successful in the ambient situation. However, if you impose background flow, it all failed. It was very, a strange situation. And later, my students, come up with the idea: we are missing something. We need an antenna to measure the ambient fluid flow. And we added this portion to check the speed of ambient, and then was successful. So if you go to the a dragonfly, I don't know whether you need only 4 wings, or so you need to consider the shape of the body. The long body will be influential. I don't know. You may need to try that.
I was thinking about UAM, because UAM, urban air mobility, right? Mm-hmm. So we are not limited to, helicopter or fixed wing. In the future, probably there are so many crazy types of the UAM. Right. And then we have to know the controller information. So I think that is a very good way to construct the controller to optimize the, the motions and stuff like that. So I think it has quite a good opportunity in the future.
Yeah.
Thank you.
Thank you.